In this tutorial, I want to show you how to use the SPI peripheral in your microcontroller to connect to an I/O expander. An I/O expander is an IC that basically lets you have access to more GPIO pins through either an SPI connection or an I2C connection. In this case, the I/O expander that I'm using uses the SPI communication protocol, and it lets you have access to 8 more GPIO pins through the SPI port on your microcontroller. So what I'm doing here is I'm driving 8 LEDs, but you can actually connect more than one I/O expander to your microcontroller. So you could actually drive up to 24 LEDs or any other type of digital input or output device with the same SPI port. So let's go check out the code. This is the schematic I'm using for this project. I have the clock of the input output expander connected to PV4. I have the CS pin of the input output expander connected to PV5. SI and SO are connected to PV7 and PV6 respectively. A1 and A0 are grounded. Reset is going to 3.3 volts. VDD is also going to 3.3 volts. And then I have an LED with a resistor of 1K at each of the GPIO pins. The reason why I'm using those pins in the microcontroller is because those pins are the ones that have the SPI functionality available. If we go to table 15-1 of the datasheet of the microcontroller, you will see that you have 4 SSI ports available. SSI stands for synchronous serial interface, which can be used as a SPI bus. I'm using SSI 2, which uses the pins PV4, PV5, PVS, and PV7. So this is my clock pin, that's PV4. Chip select or slave select, PV5. The receiving pin is PV6. The transmitting pin is PV7. So the transmit of the microcontroller goes to the receive on the input output expander. The receive on the microcontroller goes to the slave out or transmit on the input output expander. These are the locations of the pins on the board. Alternatively, instead of buying this IC by itself and doing all the connections, you can buy the SPI Demo Board. I will post a link to this board on the description below. This board is made by Microchip. I'm not affiliated with Microchip in any way. This is just a board that I like to use. So if you do buy this board, you have several SPI ICs. This is the input expander IC. So you're gonna have to jump these 4 pins. This one enables the LEDs. This one enables this IC, so you can actually select between which ICs you want, and you have an EEPROM IC, some digital pod, and other types of ICs, but the one we're using is the I/O expander, and the LEDs are located here. One thing to note before buying the IC is that you have to make sure that it has the S in the name. If it doesn't have the S, if it has a 0 instead, then that's the I2C version, which I will use in other tutorials, but the SPI version is the one that has the S in it. So just be careful about that. Let's go check out the datasheet for the input output expander. So in the datasheet of the input output expander, notice that our maximum frequency for SPI interface is 10 megahertz, so keep that in mind. The way the I/O expander works, it is pretty much like a microcontroller. You have a register that sets the directions for the pins. This is that register's address. You have another register that sets the values of the pins. That is the address for this register. So with this register, we tell the IC that we want the GPIO pins to be outputs by giving them the value of 0. We then use this register to set the outputs to either high or low. To communicate with this IC, we have to send 3 bytes. The first byte is the address of the IC, followed by the read or write bit. If we want to write to it, then that bit is a 0. If we want to read from it, then that bit should be a 1. After we send the address byte and the read and write bit, or actually it's 1 byte altogether, the address and the read and write bit, we send the register address byte. So that would be the address in this table. So these are the only 2 registers that we're going to use. So the address for this register 00, the address for this register 09 in hexadecimal. After we have sent the address of the IC and the address of the register, we need to send at least 1 data byte. And that data byte is the value that we want to put in each of the registers. So we have to send a packet of a total of 24 bits or 3 bytes. In this page of the I/O expander, we find the signal that it requires to work. So the SPI protocol has 4 modes. These are the 2 modes that the I/O expander works with, mode 11 and mode 00. This is the clock polarity. This is the edge where it samples. The mode we will be using is 00, which means that our clock steady state will be low and that we will sample on the rising edge. If you want to use mode 11, that means that your steady state of the clock needs to be high and that you will be sampling on the rising edge. So I have actually drawn here one of the signals that we need to send. So this is the signal that will turn on the LEDs. I set my CS line to low for the entire transmission of my 3 bytes. So this is my clock signal. Notice that I'm sending 3 bytes. This is the output signal of the microcontroller, or the MOSI line. So that will be my transmitting line, which is PV7. So first I send the address of the IC, which is 40. I get the 40 from the datasheet. So this is my 4, A1 and A0. If you recall from my schematic, are connected to ground, so those 2 bits are also 0. And then I send my read and write bit, which is 0. So that's my 4. This is my 0. Like I said, this is the signal to turn on the LEDs. So after I have sent my address, I have to send the GPIO address, which is 09. Then I have to send FF. So that will set each of the GPIO bits to high. Now that you know how the IC operates, let's go ahead and check out the code. So this is my code. The steps for this code have been taken from the datasheet of the microcontroller. If we go to the datasheets, initialization and configuration for the SSI, these are the steps that the microcontroller requires for you to use the SSI. So I have simply copied and pasted those steps in my code and then do what is required. The first thing I need to do is I need to enable the SSI register. Remember that I'm using SSI 2. So if we go to this register, RCG SSI, notice here that in order for me to enable SSI 2, I have to set bit 2. So that is what I have done here. Next, I have to enable the clock on the GPIO module. I'm using port B. So bit 1 of the RCG GPIO register represents port B. And in order for me to enable it, I have to set it. I also have to enable the alternate functions on the pins that I'm using. Like I showed you, I'm using PV4, PV5, PV6, and PV7. So that's 4, 5, 6, and 7. Next, I have to assign the SSI signals to the appropriate pins. Remember that a pin might have several alternate functions. So basically, I'm selecting which alternate function I need. So let's go and check out this table. So in this table, we find that for port B and for the specific pins that we're using, PV4, PV5, PV6, and PV7, we have the SSI function located at 2. If we then go to this page, which is the page for this register, then in this register we see that each of these blocks of memory represents each of the pins that we are using. Once again, remember we're using PV4, PV5, PV6, and PV7. So I have to give each of these blocks the value of 2. PV4 starts at 16. So at 16 I put the value of 2. PV5 starts at 20. So at 20 I put the value of 2. PV6 starts at 24. 24, 2. And PV7 starts at 28. So at 28 I put the value of 2. I then digital enable each of the pins that I'm using, since they will be used as digital pins. Remember that the SSI is a digital signal. Now, before we actually go ahead and configure the SSI bits, we have to disable the SSI that we're using. We're using SSI 2. The SSE bit is located at bit field 1 on this register. So if you go to this register, you will see that this is the SSE bit and it is at location 1. So this is my location, this is my value. I have to put the value of 0, so I invert it. We will be using the microcontroller as a master, so we give it this value according to the instructions. We then select the clock source. Let's go ahead and check out this register to see why I have chosen the value of 0, 0. So we have several options available. Actually only 2. We can use the system clock based on the source and the divisor, or the PIO-SC. The default clock for our microcontroller is actually PIO-SC. So it doesn't matter for this case if we chose 0 or 5, since the PIO-SC is actually the system clock. So I'm gonna go with the system clock option in case you want to change the divisor factor. Next, we configure the divisor factor by writing to this register. I believe we can write the values from 2 to 254 if I'm not mistaken. Let's go and verify that. So you can choose an even number between 2 and 254. I have chosen the value of 10, meaning that I will take this value and divide it by 10, and then that will be the frequency of my clock pin. So my default frequency, as I have shown you in a previous video, is 16 megahertz divided by 10. That's 1.6 megahertz. That means that when we produce the SPI bus signal from our microcontroller, the clock line, or PD4, will have a frequency of 1.6 megahertz. So if you take a cursor and put it here, take the other cursor and put it here in your oscilloscope, you will see that the frequency is 1.6 megahertz. In this register, we can configure the clock rate, polarity of the clock, the protocol we're using, and the data size. If you look at each of these protocols, you will see that the one we are using is the Freescale SPI. Let's go ahead and read this register on the datasheet to talk about each of the specifics. So my clock rate gives me my bit rate for the SSI. The system clock is 16 megahertz. This is my divisor factor of 10. I'm going to leave this at 0, so you can go ahead and do the calculation to see what my bit rate will be. So I have not given a value to this bit field, since that the reset value is 0, and that's the value I want to keep. My clock phase, the reset value of it is 0. That means that I will sample at the first clock edge transition. My serial clock polarity, I want the steady state value to be low. If you recall, this was the signal that I wanted to produce. My clock steady state value is low. That is why I want a 0 on this bit. My serial clock phase, if we look at the signal again, notice that I'm sampling in the first edge, which is the rising edge, since we're going from low to high. So I want to sample starting on the first edge. That is why I have selected the value of 0. First clock edge transition. Remember that this signal comes from the datasheet. Once again, you could have also selected mode 1-1, which means that you would have had to set these 2 bits to 1. But I have selected mode 0-0. Protocol that I'm using, like I said, if you go on Wikipedia or Google and see the specs for each of these SSI modes, you will notice that the Freescale SPI mode is the one that matches our application. The reset value is 0, so I don't have to mess with that one, since that matches what I want. Lastly, we can send this number of bits per transmission. So you can choose between a number between 4 and 16 bits. Since we're sending 3 bytes, I have selected the value of 8 bits. So that is the value 0x7 at bit field 0. This is where our bit field starts for this field. So that is where the 0 comes from, and the 7 of course comes from this value here. There is a problem with selecting any of these values, however, and the application that we are trying to perform, I will show you why there is a problem and how we can fix it. I'm not going to use the micro DMI in this tutorial, so let's go ahead and go to step 7. So if you recall, in the first step of setting up the SSI, we had disabled it. Now that we have set up all of the bits that are required, we go ahead and enable it again. I have created a function called write SPI, and that is what actually sends the data through the MOSI wire which would be the PV7 pin. So what I have to do is I have to put the data in the data register. So that is a byte that I want to send. I then wait for the data to be sent. If you go to this register, that is the status register, and I'm checking bit field 0. So the FIFO, that is where our data is located. If it's not empty, that means we have not finished transmitting the data. So while this bit is equal to 0, we are still sending data. So I just have a while loop there. Once it changes to 1, then we are done transmitting data. So the first thing I do is I set up the pins on the IC, on the input-output expander as outputs. This is the address of the IC. This is the IO-dir register address. Like I showed you, that is taken from the datasheet of the IC. So this is the input-output direction register. The address is 00. So that register controls the direction of the data. We want to connect LEDs to those pins, which means we want to make them an output. So I have to give the value of 0 to that register for each of the pins. So this is the value of 0, which makes my pins on the IC be outputs. In my infinite while loop, once again, now that I have set the IO-dir to outputs, I have to set the actual high or low values for each of the pins. So I send the IC address once again. I then send the GPIO register address. So that is taken from the datasheet, just like for the IO-dir. So my GPIO address controls the values, either high or low, for the LEDs. So after we send the address for the GPIO register, we then send the value for the GPIO register. I actually created a variable called LEDs that has a value of 00 initially, which means that my LEDs will be off. I then increment the value of that variable so that my LEDs turn on like a binary counter. Once they get to 255, which is when all the LEDs are on, the value will reset to 0 since my variable is only an 8-bit value, so it can only hold the values from 0 to 255. And then the count will start over again, and my LEDs will just continue to turn on and off like a binary counter. You also want to add a delay, or you won't be able to see the LEDs turn on and off. So if you recall, when we had set the value for sending 8 bits of data, I told you that we were going to have a problem with our application. And the problem with that is that since we are sending, this is the signal that our input-output expander requires. Notice that we have to send 24 bits of data at once. So we have to send all of those in one chip select cycle. The problem that we have is that we are sending 8 bits at a time. So this is how our CS signal looks. And there's no way to fix that by changing the data rate to 16 bits, for example, or to 12. It's just not gonna work. The way we fix this problem is that we have to take control of this pin, which is PB5. So we have to take control of this pin instead of letting the microcontroller take care of it. So the way we take control of that pin is, the first thing we need to do is we need to disable the alternate function of the pin. So that's my CS pin, PB5. We then make that pin an output, since we have to control everything instead of letting the microcontroller handle that pin. So on its own, the microcontroller toggles this pin, but now we're gonna have to do that ourselves. So this is the signal that is required. So before we start sending any data, we have to change the pin from high to low. Once we are done sending the 24 bits of data, or the 3 bytes, we switch it back to high. So initially we have to make the CS pin be high, then we change it to low to begin transmission. We send the 3 bytes of data, then we change it to high again after we have sent the data, so that it matches our signal. And we do that every time that we are sending the 3 bytes of data. So if you go ahead and run this program, it's still not going to work. The reason why it doesn't work is because now that we are taking control of this pin, PB5 or the CS pin, then we also have to make sure that our time before we send data and that our time after we send data matches the specifications of the datasheet. So you actually have to have a minimum, there's a minimum required time in the datasheet that you have to wait after you have toggled this pin before you can start your clock. There's also another requirement where you switch your CS pin back to high after you're done sending data. And the only way to really find out what's wrong is to look at the signals with an oscilloscope. That is actually what I have done. And what I found was that if we leave the code the way it is, then the CS pin actually changes before we send the last bit, or before the last bit is sent, or maybe it depends on the frequency also. It might send it right after, and the time between this edge and the CS toggle may not be enough. So what I have done is I have added a while loop or a for loop to increase that time so that it matches the specification on the datasheet. So this is the code that will drive the input-output expander. Go ahead and compile it and run it. That's it for this video. Thank you for watching.